Hi, Math 30-1s. Today we start into discussing trig identities. Okay, so as you can see at the beginning of the lesson, the first thing that we discuss is the difference between what an equation and an identity is. So the first thing that they mention or give an example of, okay, is this equation right here, 2x squared plus 3 equals 11. This equation will only be true, okay, for particular values of the variable x, okay? It won't be true for all values of x. So, for example, the solutions here are -2 and 2. When I substitute those values in to the equation which is given, the left side of the equation will equal the right side of the equation, okay? We call that, again, satisfying the equation. Both of those solutions are valid. When I take a look at something that's an identity, okay, as this is down here, x plus 1 squared equals x squared plus 2x plus 1. Again, we know this is an identity and it is true for all values of any variable x. So no matter what value you substitute in for x, when you add 1 to it and then square it, it'll always be equal to that x value squared plus 2 times that x value plus 1. Okay, so that is an identity. It is always true no matter what value of x you substitute in. An equation is only true for certain values of x, and that's why you solve for x in those equations. Now, some basic identities, or what we call our basic identities. And we've seen these before. We didn't really label them as identities, but now they do have that title. Sine of any angle will always be y over r. Cosine will always be x over r, and tangent will be y over x. And again, that comes from x squared plus y squared is equal to r squared. So those identities, okay, again, when we did study them, okay, come from something along these lines, right? When I had an angle, okay, that was in what we called standard position, like this here, okay? Remember, this was the x dimension, this was the y dimension, and this was the r dimension. So we're talking about that as our reference angle. So sine is the y value over the r, the opposite over the hypotenuse. Cosine is the x over the r, the adjacent over the hypotenuse, and tangent is y over x, which is the opposite over the adjacent. And then we use kind of our Pythagorean theorem, but using the variables x, y, and r because we're dealing with those right angle triangles on a coordinate plane. Okay, we've also talked about reciprocal trig ratios, which you can see here. Cosecant of x, or cosecant of an angle, is 1 over sine of that angle. Secant of x is 1 over cos of x, and cotan of x is 1 over tan of x. Okay? So again, we learned those reciprocal ratios early on, but these are what we call reciprocal identities. Okay, so when we're looking for the cosecant of an angle, I go 1 over the sine of that angle. And that's the value. So it says we can use these basic and reciprocal trig identities to prove quotient and Pythagorean identities. Before we begin doing this, okay, we're going to identify what we call identities in a particular case. So on the next page, that's the title, Verifying Identities in a Particular Case. Now, very important, and some things we want to highlight or underline here. It says, when verifying an identity, we must treat the left side and the right side separately, okay, until both sides basically represent the same value. So there is another difference between an equation and an identity. When I'm solving an equation, I'll take things from one side of the equation to the other, add or subtract values, multiply or divide both sides of the equation by particular values. With an identity, whatever's on the left-hand side must stay on the left-hand side, whatever's on the right-hand must stay on the right-hand side, and we work at both sides until, as it states in the notes there, we end up at the same expression or the same value. Now, this technique does not prove that an identity is true for all values of the variable, only for the variable being defined. Now, what that means is, or that applies to the title for this particular section, we're going to prove identities are true, but for only a specific value because they give us that value in the question. That does not mean that it is true for all values of x. When we are basically identifying or verifying an identity for a particular value, it only means that that identity is true for that value. Okay? When we want to prove an identity is always true, we cannot use numerical values substituted in for the variable. Okay? And you'll see that later on in the lesson and as we move through the rest of this chapter. So you can see in the first example here, class example 1, it does state that we're going to verify the identities, but for a specific value or for the value given. So in A, we're going to basically try to verify that tan of x is equal to sine of x over cos of x, but we're going to substitute 60 degrees in for x. So on the left-hand side, okay, that means you're going to have the tangent of 60 degrees. And on the right-hand side, okay, you're going to have the sine of 60 degrees divided by, or all over, the cosine of 60 degrees. Okay, so that's what I'm doing, substituting x being 60 degrees in for x on both the left side and the right side. Now, the tangent of 60 degrees, okay, that is the square root of 3. So hopefully you guys know that by now. If you do not, think about your 60 degree reference triangle. It'll be root 3 over 2 over 1/2, so root 3 over 2 times 2 over 1, okay, leaving you with root 3. That's how I get tan of 60 is root 3. The sine of 60, okay, again, that is your root 3 over 2, and the cosine, so divided by the cosine of 60, which is 1/2, okay? Again, remember this means divided by, so I'm actually just going to multiply by the reciprocal. Root 3 over 2 times 2 over 1, the 2's cancel, okay, leaving you with root 3. So you can see the left-hand side of the identity is root 3 and the right-hand side is root 3. I worked at both sides until they equaled the same value. Nothing crossed over. That identity is true for the value of 60 degrees. Okay, again, I cannot state that it's true for any other values of x. All I can state at this point is that it is true for 60 degrees. Okay, moving on to B. Now B is similar, okay, obviously different trig ratios, and this time they give me my angle in radian measure, pi over 6. So when I go to the left-hand side, this is going to be the tangent of pi over 6, and I'm going to square that value. Remember, tan squared of x is the same as tan of x squared, okay? And then I'm going to add 1. There's the left-hand side. The right-hand side is simply secant of pi over 6 all squared. Okay, so I've substituted the value of pi over 6 in for x on both sides. Now, tangent of pi over 6, so that's your 30-degree angle if you're thinking in degree measure, okay, and that's going to end up being root 3 over 3. Again, hopefully we know that value by now. Okay, if we don't, we can always calculate it by knowing our special triangles. So I have root 3 over 3 squared plus 1. On the right-hand side, secant of pi over 6 is 1 over cos of pi over 6, right? And it's squared, so I have to square this. Okay, and then I keep working on both sides. So on the left-hand side, root 3 over 3 all squared would give you 3 over 9, which is 1 over 3. And I add 1 to that, so 1 over 3 plus 1, which is equivalent to 3 over 3, gives me a final value of 4 over 3. On the right-hand side, I'm now going to have 1 over, I have to square cos of pi over 6, so that's root 3 over 2, and I have to square it. Okay, so when I do that, and I just got to move up here because I've got some more calculations to do, this will be 1 over root 3 squared is 3 over 4. Again, remember this line means divided by, so 1 divided by 3 over 4 is equivalent to 1 times 4 over 3, okay, which also gives me a value of 4 over 3. So 4 over 3 on the right-hand side, 4 over 3 on the left-hand side. Okay, again, same basic principles. I worked at the left-hand side of the identity, I worked at the right-hand side of the identity, they ended up equaling the same value. So again, what have I proven? I've proven that that identity, tan squared of x plus 1, is equal to secant squared of x, but again, only for the value of pi over 6 in radian measure at this point. Okay, again, I can't say that it's true for any other values of x. So proving the quotient identities and the Pythagorean identities. So we can use identities to derive or come up with other identities. When proving an identity, we must treat the left-hand side and the right-hand side separately. Okay, we know that. And we work until both sides equal, in this case, the same expression. May not be the same numerical value, it's going to be the same expression because we're not substituting values in. Remember, do not write LS equals RS, which is left side equals right side, at the start of a proof, and do not move terms from one side to the other. So class example 2 looks like this. Use the basic identities, and those are your x, y's, and r's, to prove that tan of theta is equal to sine of theta over cos of theta. And again, this is just a restriction, okay? This doesn't do anything when we are trying to prove it. It's just stating that this denominator obviously cannot be 0 because we're dividing by it. Explain why there is a restriction, cos of theta can't equal 0. Well, I guess I just did, okay? We can't have cos of theta equaling 0 because we're dividing by that expression. And if it ends up equaling 0, then everything is undefined, okay? So we can't have that. That's where that restriction comes from. So what do? Well, I work with the left-hand side. So the left-hand side, again, is tan of theta. Now, in terms of x, y, and r, tan of theta is always y over x, opposite over adjacent. The right-hand side, okay, is sine of theta all over cos of theta. Now, sine of theta is always y over r divided by cosine, which is x over r. Again, this line between the expressions is division, so that is equivalent to y over r times r over x. Okay, hopefully you can see the r's will cancel out and leaving you with an expression of y over x. Okay, so on the right hand side, y over x, and tangent on the left hand side is also y over x. Now in this case, I did not use any numerical values to prove that this identity was true. Okay, I only used variables and expressions, so therefore this identity I can now state is true for all values of x. Okay, moving on. Same thing here. Use the basic identities, so x, y, and r, to prove that 1 plus tan squared of a equals secant squared of a. So all they do here is they use an a instead of a theta or an x, okay, to represent an angle. So I'll work on the left-hand side, obviously, and then the right-hand side separately until they end up equaling the same expressions. So the left-hand side is going to be 1 plus, now, tan squared of a. Well, tangent, we know, is y over x. And I have to square it. So there is 1 plus tangent squared of an angle. Okay, so this becomes, let's go equals 1 plus, so I square that, that's going to be y squared over x squared. Okay, y over x squared is y squared over x squared. Now I want to add those two things together, so they need a common denominator. So the number 1 will become x squared over x squared plus y squared over x squared. Okay, so come up here, and this will end up being x squared plus y squared all over x squared. And we know that x squared plus y squared is equal to r squared. Okay, that's like your a squared plus b squared equals c squared. But again, on a coordinate plane, so x squared plus y squared is r squared. So I end up with r squared over x squared. Okay, so that's my expression on the left-hand side. So let's see what happens on the right-hand side. And sometimes I have to go back and tweak what I did or alter the expression a little bit so they look the same, but I'll work towards that r squared over x squared here. So on the right-hand side, I have secant squared of a. Well, that is equivalent to 1 over cos squared of a. Okay, that's the reciprocal. So therefore, this is 1 over, and we know cosine is always x over r. So this is x over r all squared. So this will become 1 over x squared over r squared. Again, this line here means division or divided by. So this becomes 1 times r squared over x squared. Okay, and obviously that ends up being r squared over x squared. So I ended up with r squared over x squared as the final expression on both the right and left-hand sides of the identity. Okay, so we're good. I proved that it's true, and again, I can now state it's true for all values of x because I never used a numerical value in the substitution process. Now, in the same way that basic identities can be proved, so can the following. Quotient identities. Tangent is sine over cos, and cotangent is going to be cos over sine. Okay, and that is due to the fact that tangent is y over x, and we know sine on the unit circle is just y, and cos on the unit circle is just x. So y over x, and cotangent, obviously the reciprocal of that, so x over y. Now, Pythagorean identities. Sine squared plus cos squared of x equals 1. 1 plus tan squared of x is equal to secant squared of x, and 1 plus cotan squared of x equals cosecant squared of x. These identities, again, good to know, okay? Specifically the first two, you'll see those ones quite often. All of these identities, okay, are given to you on a formula sheet. And you guys, my class anyway, will see these on the back page of the workbook. Okay, so if you flip to the back page of the workbook, basically the whole right-hand side of that formula sheet is trigonometry. And starting about a third of the way down to the very bottom, okay, are all your identities that we are going to learn from now and then over the next 4 or 5 lessons. Okay, and we're going to use these identities, as it says, in several ways, and should be remembered in trying to prove more difficult identities as we get more complicated lesson to lesson here, okay? So you can see that if I start up here at sine squared of x plus cos squared of x equals 1, okay, other forms of that identity might be like this. Well, that means sine squared of x could be equal to 1 minus cos squared of x, okay? Or from that as well, you could say cos squared of x is 1 minus sine squared of x. So those identities there okay, are derived from that original identity of sine squared of x plus cos squared of x equals 1, okay? And again, when we say that we're dealing with identities, what does that mean? Well, that means if I come across a question where I have, for example, sine squared of x plus cos squared of x, so I see that expression, I can simply replace it with 1 because they're equivalent to each other. They're identities that are always true. Okay, so moving on underneath, it says we use the basic trig identities in terms of x, y, and r to only prove the quotient Pythagorean identities. You will be asked to verify the remaining quotient Pythagorean identities in the assignment, and before considering more complex identities, you need to review some skills in simplification and factoring, okay, which will help with the proofs. So that's what we're going to take a look at here for the remainder of this lesson. Okay, the instructions here read like this. Express each as a single trig ratio. Use a graphing calculator to verify. So what that means is that when I graph to verify that an identity is true, what I would do is I would graph the original expression that is given to me. Then I would graph the final expression that I come up with. And when I graph it on my calculator, I will only see one graph because the calculator will graph the original function or expression. And then if the last or my final answer or expression is equivalent and I did it properly, the second graph will graph right over top of the original one because it's the same. It's just simplified. So you will only see one graph because the second graph or y2 graphs right over top of y1. Okay? I will show you that or write that out here at the end of the question once I get my final expression or trig ratio. So what I want to do here is I want to add sine squared of x over cos squared of x plus 1. So we know that when we add, we need a common denominator. The first expression will stay as sine squared of x over cos squared of x. Okay, but the number 1, if I want to add it to that, must have a common denominator of cos squared of x. So I multiply numerator and denominator by cos squared of x. Okay, so there's the number 1, cos squared of x over cos squared of x. Now that I have a common denominator, I can combine the expressions in the numerator, so sine squared of x plus cos squared of x, all over that common denominator of cos squared of x. Okay. Now, here's your first look at using an identity. In the numerator, I have sine squared of x plus cos squared of x. So if you know that already, that's great. If not, you flip back to the previous page or to your formula sheet at the back, and you'll see sine squared of x plus cos squared of x is equal to 1. That's an identity, so I replace it. So I end up with 1 over cos squared of x, and a single trig ratio that's equivalent to 1 over cos squared of x would be secant squared of x. And there you go. It's a single trig ratio. So now, when I was talking about proving this using a graphing calculator, what I would do is I would graph y1 as, you'd have to go sine squared of x over cos squared of x plus 1. That would be your y1. Then you would have to graph your final trig ratio or expression, which would be secant squared of x, which you would graph as 1 over cos squared of x. And you should only see one graph, okay, because they are, in essence, the same expression, okay. Now in B, we have sine of x plus cotan of x, cos of x. So a good rule of thumb, okay, to always look at when you're dealing with an A is whenever we have cotan of x's or tan of x's is to rewrite them in terms of cos and sine. So what I mean by that is the following. I'll keep that first sine of x as it is. Plus, well, I know cotangent of x is actually cos of x over sine of x. So there is the cotan of x, and I'm still multiplying that by the cos of x. Okay, so I rewrote the cotan of x as cos of x over sine of x. Next, what I do is I multiply those two expressions together, the second one anyway. So I have sine of x plus, now I have cos squared of x all over sine of x. Okay, so that was me just multiplying cos x over sine of x times cos of x. Again, now I want to add these two expressions together, so I need a common denominator, which will be sine of x. So I multiply numerator and denominator of the first expression by sine of x, giving me sine squared of x over sine of x plus cos squared of x over sine of x. The two expressions now have the same denominator, so I'm able to combine the expressions in the numerator together. Sine squared of x plus cos squared of x all over sine of x. Okay, and again, sine squared of x plus cos squared of x is 1. So this is 1 over sine of x. And 1 over sine of x is equivalent to cosecant of x. And there is your single trig ratio. Okay, so that question took up a little bit of room, but okay, that's what you're going to have to do. Okay, so again, the key there, when we see cotangents or tangents, we normally rewrite them in terms of sine and cos. Okay, and that will usually help us combine expressions together or simplify. Okay, class example 5. Express 2 tan of a over 1 plus tan squared of a in terms of sine of a and cos of a and write it in simplest form. So again, this is ideally really what I was talking about in B of the last example. I want to replace the tangents with sine over coses. So in the numerator, okay, I'm going to have the following. 2, and instead of tan of a, I'm going to write that as sine a over cos of a. Okay, because remember, tan is sine over cos. That's the numerator. The denominator is going to be 1 plus, so I have tan squared of a, well that's going to be sine squared of a all over cos squared of a. Okay, so again, I've started out by doing exactly what they said, writing the tangents in terms of sine and cos. Okay, next step. So in the numerator, when I multiply the 2 times sine a over cos a, this is going to be 2 sine a all over cos of a. Okay, and remember that's because this 2 is like a 2 over 1, right? And in the denominator, what do I have there? Well, I need to combine these two expressions together by adding, so I need a common denominator. Again, that's going to end up being cos squared of a over cos squared of a plus sine squared of a all over cos squared of a. Okay, so what I'll do is I'll leave the numerator alone for right now. So this is 2 sine a over cos a. But the denominator, hopefully you can see what's coming, is when I combine those numerators together, you're going to have cos squared of a plus sine squared of a. Well, that's 1. That's our identity, right? So that's 1 over cos squared of a. Now again, this line here means division. So what I end up doing is multiplying by the reciprocal. So I'm going to have 2 sine a all over cos a, there's my numerator, and now I'm going to multiply by the reciprocal in the denominator. Okay, so I'm going to multiply by cos squared of a all over 1. So what happens there is that with this squared here, one of those cancels with this cosine down here, and that leaves me with 2 sine a cos of a. Okay, and there's your simplified expression, okay, in terms of sine and cos. Okay, moving on. Okay, so now practicing a little bit of factoring here. It says factor the following trig expressions. So when you take a look at this first expression, okay, the first thing that we notice, okay, is that I have 2 terms and there's a 3 in front of both expressions. So I'm just going to factor that 3 out. So factor the 3 out. This is now cos to the exponent 4 theta minus sine to the exponent 4 theta. Okay, now this is actually a difference of squares. Okay, I can take the square root of each of those terms. So this is going to be cos squared of theta minus sine squared of theta, and then cos squared of theta plus sine squared of theta. Okay, now again, at this point, a lot of students are very happy, like, oh, I took out a greatest common factor, I've done a difference of squares, I did a great job, I must be done. And it's right, you are right, you did a great job, but we're not done yet. And the reason being is this, I still have this 3 out front, okay, but this cos squared of theta minus sine squared of theta is still a difference of squares. You can write it as a difference of squares again. It's cos of theta minus sine of theta and cos of theta plus sine of theta. Okay, this cos squared of theta plus sine squared of theta, that's an identity. We learned today that that's just the number 1. Okay, so now 3 times 1, well, that's still just 3. So 3 cos of theta minus sine of theta and cos of theta plus sine of theta. Okay, and I just noticed as I was writing, I should not have a squared there. Okay, so this is cos, oops, apologize. That's simply just cos of theta, not cos squared. Okay, so your final expression is 3 times cos theta minus sine theta, cos theta plus sine theta. In B, okay, again, I have 2 terms. I have sine squared of theta, cotangent squared of theta. So what I can factor out is sine squared of theta, okay? You can see that that is the same between those two terms. So I factor out sine squared of theta, leaving me with 1 plus cotangent squared of theta. Now, if you look on our identities that we learned today, or you flip to your formula sheet at the back, 1 plus cotangent squared of theta is equal to cosecant squared of theta. That's an identity. So I replace 1 plus cotangent squared of theta with cosecant squared of theta. Now, cosecant squared of theta is 1 over sine squared of theta, isn't it? They're reciprocals of each other. So now really you have sine squared of theta times 1 over sine squared of theta. Okay, these expressions cancel out, so you're really left with a value or an expression that is just equal to 1. Then that's it. Okay, so again, I know it's a lot to take in. Identities are intimidating, okay, and they just take a little bit of work, okay, in terms of you using them. And again, I know it's been said a million times in math, but the more that you do, the more comfortable you will get with it, because you see the same expressions and the same processes over and over and over again. Okay, when it becomes overwhelming is when you don't work with this stuff, and then you try and sit down and just do it for the first time on a test or, you know, some kind of formative assessment that you get. So really practice it. Really try the homework, okay? And again, anytime you have a question, screenshot it, send it to me via email, and I will get back to you with, you know, maybe some helpful hints or do the question for you, walk you through it, those types of things, okay? But please practice them. They just get more